No, I've got none.
You didn't get any chocolate for Christmas?
That's
There you go.
Trying to think. I don't think my family got me any chocolate.
They don't know you. They don't know you supposed to be do.
No, they don't. No, that's all I like.
I got you chocolate, remember?
Yes, I do.
Did you eat all of it?
Not yet. No.
You better remember.
Yeah.
Can we also get guns for you?
That would be fine. Yeah.
Oh.
All right. So anyway, let's just begin today with some definitions. Some of this you'll remember from Chem 1, and then some of you, depending on how far your Chem 1 teacher got, you'll know some, and some of you won't know some of it. So we'll all be together here at the end. In general, at the very core, acids will increase the hydrogen concentration of water somehow, and bases somehow will increase the hydroxide concentration of water. There's different ways that that can be done. We dealt with acids and bases back in chapter 4. Stoichiometry. We really thought only of Arrhenius acids and bases. And we'll see in this chapter, we won't focus at all on Arrhenius, we'll just deal with Bronsted-Lowry. But just to recall, Arrhenius acid, this is the first definition that was ever developed for what an acid and a base are. Acids are things you put into water that release hydrogen ions. They have hydrogen ion, they just give them off in water. And bases are anything that has hydroxide ion, you put into water and it gives off hydroxide. Following the definition of what an acid and a base are. As people learn more chemistry, though, they realized it's possible to have a base without using some hydroxide compound. You can put something into water that will raise its pH, which means it's basic, raise it above 7, but it doesn't have hydroxide. And so a new definition of acid and base were kind of derived. And this is two different American chemists. I think they were both American, Bronsted and Lowry. The Bronsted-Lowry definition or theory about acids and bases. Acids are pretty much described the same way as Arrhenius had. They're anything you put into water that increases the hydrogen concentration. However, a base, that definition is very different. According to Bronsted-Lowry, a base is anything that you put into water that will accept a hydrogen ion. And that's different than giving off a hydroxide. And this is where we're all going to have a little bit different experience depending on where we were at the end of last year. Because last year in Chem 1, everybody was doing acids and bases, just got to different places. You may have talked about Bronsted and Lowry acids and bases. If you have an acid like this, HNO2, strong acid or weak acid?
Strong. Or no, it's weak. Wait, but can it break the
Back in chapter 4, we talked about the strong acids.
Oh, we forgot.
No, you didn't.
Yeah, so it's weak.
Nathan?
HNO3 is strong.
HNO3 is a strong acid. Nitric acid, yes. And then 5 others, HCl, HBr, HI, HClO4, H2SO4. This is not one of those, so it's weak. If it's a weak acid, that means that, let's see, that means it's not strong. What was a strong acid again? Every single molecule in a strong acid releases a hydrogen. Every single molecule. So that once a strong acid is dissolved in water, you don't have any of that acid molecule left over because all of them have dissociated. When you have a weak acid, it's going to also release hydrogen ions. The difference is that arrow right there. Only a few of the molecules release hydrogen. Most of them stay together. Most of them stay together. By far, most of them stay together. But a few of these are released. So we'll have a small additional concentration of hydrogen, which makes this thing an acid. This is considered the acid because, look at the definition. It donates, it offers up a hydrogen, releases it. The NO2, in this case, is considered its conjugate base. It's a conjugate base because, looking at this arrow again, this reaction, if it goes back to the left, what is this thing going to be doing? It will be accepting a hydrogen ion. Yeah? So these two are kind of pairs. They kind of work together. When it's going to the right, this is releasing a hydrogen, making it an acid. When this reaction is going to the left, this substance is accepting a hydrogen that makes it a base. Now, because this is a base, in just this situation, if I have a nitrite compound, and I put a nitrate compound into water, not even HNO2, but like sodium nitrite, because it's a base, it will increase the concentration of, well, it does increase the concentration of hydroxide, which would raise the pH. Because it can accept a hydrogen, it's able to accept a hydrogen. So this is really going to be our working definition of what an acid and a base are. If you don't like it right now, you'll use it a lot and you'll eventually just get used to it and not even think about not liking it. Weird. Okay, now when we deal with strong acids versus weak acids, I was just talking about the difference between a strong acid and a weak acid. I try to make it very obvious with this arrow. I used the thickest font that I reasonably could to show this is a one-way reaction. It goes that way, it cannot go that way, as illustrated by the very bold arrow. This is what strong acids do. Every single molecule of HA dissociates. There is no equilibrium. It doesn't dissociate some or a lot and then stop. It dissociates completely, 100%. There was a lecture given by a very brilliant chemist that described strong acids better than I ever could. And I want to play, I actually recorded or have a recording of this chemist. And if I could, I'm going to just play a short part of it so that you can get the idea, if I can. Let's see what I have to do here. My little, oh, here it is. See that little icon? That's what I was looking at when I, okay, listen to this. This is the description of a strong acid. Oh, come on. I'm afraid I'm going to blast you out of here. I wonder if the computer's on mute. Oh, my battery's going to die too. Oh, shoot. It's not on mute. Well, I got 45 minutes remaining. We could be here for a long time.
Yeah, but if it says
Okay,
45,
maybe.
it's usually less than 45. Yeah. It's usually like 10.
Oh, yeah.
Because this is the last battery.
There she is. This is the lecture by a brilliant chemist describing what happens with a strong acid. This is Taylor and boyfriend. They're never, ever, ever getting back together. Great finish, Taylor.
I was really like,
You were expecting some crotchety old chemist, right? But that is exactly what happens when I hear that song. I think strong acid. The H and the negative ion break apart, and they're unable. They can't get back together, just like the ex-boyfriend. It's over. And now this is, I mean, we laugh, and I try to make a kind of a joke about it so you remember it. But as we go through, we do this chapter and then the next chapter on buffers. That is one of those really key concepts to understanding acids and bases, is that whole notion of, for those 6 strong acids, remember there's only 6 of these things in the world. For those 6, that conjugate acid, like the chloride ion, the bromide ion, the nitrate ion, they are not able, when they're in solution, they're not able to take a hydrogen. And I'll remind you of that numerous times as we go through these next couple of chapters. Real big. Okay, now, in contrast, and you saw it over here, a weak acid like HNO2 is going to slightly dissociate. We get that equilibrium sign there, and that means that we'll have an equilibrium constant for these reactions. For the weak acids, there's going to be an equilibrium constant. We're going to call it Ka. The little subscript A represents, and I have it right there, K with a little subscript A. It's still products over reactants, but it's going to indicate what the strength of the acid is. The bigger the K value, the more it goes to the right, the stronger the acid. So we'll be able to compare acid strength just looking at Kas of acids. Remember, the constants, we'll have a table. There's a table in our book, in the appendix, right after the thermodynamic constants, that has the Ka values for lots of different acids. You'll be looking back there. Okay, and then also I have on here how bases, their strength is determined. There. So I'm symbolizing a base with a capital B, and that B just means any Bronsted-Lowry base, anything that can accept a hydrogen. And you see what it's doing. It, when you put it into water, will take a hydrogen ion from the water. So water is not incapable of breaking apart. It very much can break apart. It doesn't, it's not crazy about it, but it can. So the whatever the base is can accept the hydrogen from the water and make an Hb plus molecule, or not really molecule, but ion. And then what's left of the water molecule after it loses a hydrogen is just a hydroxide ion. So even if B doesn't have any hydroxides in it, you put it into water and suddenly you have this increase in the hydroxide ion concentration right there. It was because the water is breaking apart and increasing hydroxide. So it kind of indirectly increases the hydroxide concentration. Emily?
How would a strong base look? Like the equation for it.
Now, there's only a few strong bases, and those, do you remember what the strong bases are?
And one of them's lithium or allyl.
Yeah. The group 1 hydroxides and the bigger group 2 hydroxides. So strong bases, there's really not even a reaction. There's NaOH, sodium ions,